Huang. So he's well known to us. Come and give many seminars at CLSP before. So just to remind you of his background, he graduated from Shanghai Jiaotong University as an undergraduate, where he was summa cum laude honors for his thesis on probabilistic K-best parsing for classical and modern Chinese. He did his PhD at the University of Pennsylvania, where he moved beyond K-best parsing into forest-based algorithms for NLP. He graduated from the PhD at Penn in 2008, and since then he's been doing a variety of things, including being a researcher at Google, and now he's currently research faculty at the University of Southern California in the Information Sciences Institute. And there he's been teaching a variety of classes, including algorithms, machine translation, and several AI and NLP courses. And beyond that, his research is really awesome. So he frequently either wins best paper awards or has most of his papers nominated for them. So without further ado, I give you Liang.
Thank you, Chris. Thanks for having me. So it was my great pleasure to be here to give the third CLSP talk in the past 4 years. So this is my third talk. I gave the first CLSP talk in 2008 and second one in 2010, and this is my third one. But this talk is slightly different. It's kind of different from previous two talks in the sense that today I'll focus more on linear time incremental algorithms for search, both search algorithms and machine learning algorithms for language understanding and translation. So what I mean by linear time incremental is like human processing. It's like how human beings understand a sentence, like I associate with tuna from Japan. We do it from left to right and do it in linear time. So we're going to see a lot of that in today's talk. Basically, the idea is to simulate that kind of parsing and translation on computers. And how can we make computers as smart as human beings in its efficiency and incremental processing of natural language? Okay. So I dedicate this talk to Fred, to the memory of Fred, who hosted my previous visit to CLSP about 2 years ago, but he tragically passed away. So he was very supportive to my work in general, so I dedicate my talk to him. And so before any technical details, I always convince you guys that NLP is a hard task. And to convince you that, it's like, we'll give you an example, like I use sushi with tuna and ask you, how many interpretations can you think for this sentence? How many meanings are there? Well, there's a default meaning, that is you eat sushi with tuna, but there's some other more creative meanings, more creative interpretations. Can anybody tell me? Any ideas? Yeah.
I eat sushi with my friend tuna.
Yeah, exactly. That's one of the ideas. What else? Yeah.
I use tuna as a spoon for eating
exactly.
sushi.
So that's the second. So this is the first part, which is tuna with sushi together. But there's a more creative one, which you use tuna as chopsticks. But that one is a different parts from this one, which is attach this PP with preposition with to eat instead of to sushi. So that's using chopsticks. And the third one is what you said. So you kind of eat sushi with tuna as your friends. So there are a lot of other creative ways to think about it. So basically, that's structural ambiguity problem, and that's one of the hardest cases in NLP. And there's another sentence which I showed a lot in my previous talks here. So I saw her duck, and that's the default meaning. And what else?
She's ducking.
Sorry? Yeah, that's the second one. Yeah. And what else?
I saw her look out.
Sorry?
I saw her look out.
No, that's the second one. Yeah. The third one is what you said. I saw her duck. No, that's the real bad one. But that's creative. But so that's different types of ambiguity. That's called lexical ambiguity, because that's basically the different interpretations of different meanings of the word soul and different meanings of the word duck. Right? So that's totally different. But if you combine, lexical ambiguity and structural ambiguity, you got something even worse. So what if I say I saw her duck with a telescope? How many meanings are there? I would say at least 6. At least 6, because you can attach this with a telescope to either duck or to saw. And in the extreme case, you say, okay, so I can use a telescope as the saw to saw her duck, or I can saw her duck where the duck has a telescope on her neck or something like that. So you can branch it off, you can attach it differently, or if I say I saw her that with a telescope in the garden and so on and so forth. You got many, many more interpretations. So you got basically exponentially more interpretations as we go longer and longer in the sentence. So that's the ambiguity explosion problem. It's basically the same problem as the combinatorial explosion problem in theoretical computer science. So in my view of computer science, like half of computer science is trying to tackle this problem. It's basically exponential versus polynomial NP versus P problem. And we're basically doing the same problem in NLP. So we're just trying to tackle ambiguity explosion in natural language. And throughout this talk, I will use a lot of ideas from theoretical computer science to try to borrow those techniques to help NLP. So that's kind of a general research plan. And I'll show some other funny examples. So when I go back to China, I saw a lot of science like that. So this is currently an ATM machine, but the science is like help on some terminating machine. But if you really understand Chinese, it's actually not that bad. It's actually, if you just look at a glass, it's self-help terminal device. But it's not something you can help yourself to terminate yourself. So translation has to be done in context, and more importantly, you have to understand the source sentence before you translate. So my view of translation is that translation requires understanding. So some people say translation doesn't require understanding, you can just do word by word or phrase by phrase. My view is totally different on that. And I can, if you're still not convinced, I can show you more examples of translation without translation, and you'll see a lot of that in China. So at least they tell you to do it carefully if you have to do it, right? So there's tons of that. And this is exactly the same translation if you feed it to Google Translate. This is for like a phrase-based translation. And poison is evil rubbish. And or short-sighted treatment. It's not that bad. It's really treating short-sightedness. So, or one of my favorites is like that. That's from my hometown. When I go back to Shanghai, I took a metro and I saw that. So I wonder, like, if you were already stolen, how can you then call the police at once, right? So, but my all-time favorite must be this one, which is silver era. Which is basically, so there's a restaurant in China, and the restaurant owner wanted to have some English title, English name, but just unfortunately on that day, Google Translate or some other translation server is down for some whatever reasons, maybe scalability reasons, and he didn't know that. He just thought that translate server error was the name of the restaurant. And I like this not just because it's funny, but also because it's the clear evidence that MT is useful in people's daily lives. Some people say, you guys do MT, it's not going to be useful in the next 10 years. See, people are already doing that in their daily life. And the second reason I like this example is because it demonstrates that scalability or efficiency is really important in machine translation. I mean, the point that, the reason that this server is down is because it doesn't scale. So, and we want to design more efficient algorithms which use less memory, which runs faster, so that it will never be down. So we'll now see that in the future. Okay, any questions? Yeah, just stop me if you have any questions. So, we're going to basically ask two questions in this talk. So basically, can computers be designed to understand natural language the same way that we human beings do? So basically, we want to understand left to right in linear time incrementally. And secondly, can computers then, based on understanding, translate natural language sentences into some other language like Chinese or French the same way as human beings do? And I want to argue that human beings translate in two steps. We first understand it, and then we generate from that meaning. So basically, we understand it. Okay, so maybe that meaning, sushi from Japan, and then we generate Chinese for that. So that's the two key questions we're going to kind of tackle in this talk. And the first part is how can we design fast and accurate disambiguation of the parser in this exponentially large explosion space? So we're already convinced that the number of interpretations explodes exponentially. But how can we still design fast and fast meaning linear time and accurate parsers in that huge space, more like the way human beings do? So that's the first part of this talk, and I'm going to switch to that. And then we're going to come back to the second question in the second half of this talk. Okay, so let's take a deeper look. So this is human parsing, and this is the way computers do parsing right now. So this is the current state of the art. It's like CKY parsing. And CKY parsing is cubic time. So it's kind of fitting a chart, between bottom up. And I would say nobody would do that, in practice. We as human beings, we cannot afford to read a newspaper in cubic time. I mean, can you do that? Some people say you can read each sentence in cubic time, not the whole newspaper in cubic time. I would say even that is not possible, because if you read it like Wall Street Journal, the longest sentence in Wall Street Journal is like more than 100 words, right? They tend to write very long sentences. So you can't afford to do that. So you have to be linear time, just like human beings. And the other example is compiling. So if you have a C++ program, to compile it, it's also linear time. But that's different because that grammar is designed to be, first of all, unambiguous, because you cannot use an ambiguous language. And secondly, linear time possible using some like AR methods and compiler theory. The question is, can we do something similar to compilers or to human beings for natural language? And it's very difficult because natural language is fundamentally inherently ambiguous, whereas programming language are designed to be linear time possible and unambiguous. So that's the difficult task. And so here's the overview of the state-of-the-art of computer parsing. And right now in this block, we have principal search, but slow, so cubic time CKY like this kind of shape. Or here we can do greedy search, but fast. So fast, but greedy search. So incremental parsing like the way we did before. And it's greedy, it's lossy, so the search quality is not that good. So we're wondering if there's anything here that is both principal search, like dynamic programming, but fast, like linear time. So can we do something in that box? That is very difficult because to do dynamic programming exactly, you have to be cubic time, at least for common programmers. So you have to be doing something approximate, So we're going to talk about this work that is a linear time incremental dynamic parser with approximate dynamic programming. So it still searches over exponentially large space, but in linear time. So that is very highly non-trivial task. And then if we zoom out to a bigger picture, so that's my long-term research plan, which is goal. So my inspirations come from human processing of natural language, or computer processing of programming languages. In both cases, it's fast and good. So we kind of bring these technologies from compilers and inspiration from psycholinguistics to help this work. So we'll design more like these two guys. And to do that, we use a lot of algorithms from theoretical computer science, and also a lot of machine learning because we want to learn those from data from tree bank, for example. But more recently, I've been doing that direction as well. So to give back to machine learning. So not only I use machine learning techniques, but I also develop novel structural learning algorithms inspired by NLP research, but this is more general than NLP. So it could in principle be applied to, say, computational biology or computational any structural problems. There are a lot of other structural problems beyond NLP, so that's another direction of my research. So that's my long-term plan. Any questions? Okay, so here's the outline of this talk. So basically, I'll talk about 3 problems. First, how do you do parsing? How do you do fast linear time dynamic programming? That's the search problem. And then we're going to talk about how to learn this parser. So learning problem of the parser. So these 2 guys are basically on parsing. And then we're going to talk about one application that is, if you have a very good parser, very fast and accurate, how can you apply it to machine translation? And then we can look at some future directions. Okay, so now on to incremental parsing. So before I talk about any details, let me do some overview of the results. So at the end of the day, after the technical details, we arrive at this parser, which is really fast in linear time, according to sentence length. So this x-axis is how many words you have in a sentence. So these are Charnier parser, the Berkeley parser, Rand-McDonald's, and the T parser. Those are kind of more popular parsers, but they are cubic time or close to cubic time or quadratic time. And we are linear. And not just we are linear, but we are actually linear with a very small constant factor. So we are linear, and we are really fast. Even with the Python implementation, these guys are C and Java implementations. So we are really fast in terms of speed. And we also manage to search over exponentially many parsers for sentences. So if your sentence gets longer and longer, the number of parsers we consider to parse in this parser is exponentially more. So this is actually an exponential scale. So we managed to search over exponentially large space in linear time. That is very difficult. Any questions? Sure.
Yeah, so you don't have things like mult parser on the graph?
Mult parser is roughly like this line, but it's this line, basically.
Yes.
So mult parser is linear, but it only searches over a linear number of trees, or actually constant number of trees for beam search. So if they have beam of 10, they only look at 10 trees. And I can look at exponentially many trees with the same beam size. So I also do beam search, which I'll talk about in detail, but within this beam, you do exponential. I'll talk about it in detail. Any questions? Okay, great. So let's look at parsing in detail. So we'll focus on dependency structures just for simplicity of presentation. It actually can work in constituting parsers. So here's the sentence I see sushi with tuna from Japan restaurant. It explodes exponentially, and these are the different dependency attachments. And we're going to look at incremental parsing first. So the idea is coming from the compiler theory, shift reduce parser, which is one of the oldest incremental parsers. So we're going to look at how we can parse this sentence incrementally. So we have a stack and a queue, and each time we do either shift or reduce. Okay. So first we have to shift I and shift each. Now, when we have two guys, we can do a reduce. So this is left reduce. Basically, I is a left modifier or subject of the verb eat. And then we have to shift again because we have only one tree on the stack. And then we have two guys. Then we can reduce this sushi as an object of verb eat. So that's one possibility. Another possibility is to shift without before you reduce the sushi. So you can either do reduce or shift based on this number 4 step. And that's a conflict. That's basically you have a choice. And when you have a choice, it's called a shift reduce conflict. It's a kind of central concept in compiler theory. And compiler theory says you want to design a programming language grammar so that there's no shift reduce conflict in your table. But it's totally impossible for natural language because it's inherently ambiguous. So we have to face a lot of shift reduce conflict in practice, right? So because of ambiguity. And how do we choose between either shift or reduce? Any idea how do we choose between them? So we use machine learning to assign scores to these two actions. So we can say maybe according to the data, reduce is more likely than shift for them. Okay, but that's not the important. The important thing is we just assign some scores to these actions and we choose the best one, for example. Then we can do greedy search. So each state, so if you start from here, you can do shift reduce, left reduce, or right reduce, and you choose the best one to follow. So greedy basically is really bad in the sense that you commit to the best choice, and you cannot revise it, right? So you commit to the best choice, and you go next step, you commit to the next best choice, and every time you just keep one. So that's greedy. And if you do that, that's the way people usually do incremental parsing before my work. And this best is defined by a score, and you search for just one path in this huge space. So if this is the exponential space, of course it's exponentially large, you only have one path. This is just not going to work very well, right? So people do something better than that. That's called beam search, which is very much like that. It's just kind of a relaxation of greedy search. It's less greedy than greedy, but still greedy in nature. So instead of keeping the top one, hypothesis, you keep top, say 5, or top 10, so that you can sometimes use non-one best interpretation later. So you can recover from some of the bad choices initially. So if you do beam of more than one, it's going to work a lot better because you search over kind of narrow beam into this huge space. So maybe this beam is 5 for them. But it's a kind of constant size beam. So it's kind of, you have a torch into this thick forest, and that's why it's called beam search, basically. But if you look at this shape, it's exponentially large, and you still touch only a tiny fraction, a constant number. It's a very tiny fraction of the whole search space. So this search is going to be very bad either. So what's our idea to improve upon that? Any ideas? So we're going to do something fundamentally different that we're going to do dynamic programming. So this is the space, exponentially large. And to do dynamic programming, our goal is to transform that exponential space into some polynomial size. And the key idea of dynamic programming is to share a common subproblem. And how do you share? So if you can define some equivalence relations between states. So if you claim that maybe this state and this state are more or less the same, so maybe some difference about which I would not care in the parser, then I can merge them. So if I can define some equivalence relations, then I can merge them into this shape. So by merging equivalent states. And this shape is now kind of polynomial size. It's polynomial in the sense that you imagine this is stem. So that change is the single most important idea in this work. That is from exponential to polynomial by sharing the equivalent states in dynamic programming. So basically, after you do that, and you still do a beam search, the same beam, but now the same beam contains exponentially many paths already in this very small beam. So it's the same size beam, but it used to be just 5. You just 5 guys. Now it's a beam of 5 again, but it's like millions of them in it, right? So it's millions of paths in this very narrow beam. It's because each state in this narrow beam corresponds to exponentially many original states in the original space, which is exponentially large question.
And in each DP state, are you saving a pointer to the best scoring path that's that one?
Yeah, not just best, but actually all alternative paths. So that's why. So you have 2 paths to compute this thing for now. Now, if you do that, this state is actually exponentially large, but you kind of shrink them. You kind of manage to represent them in a small space. And that's exactly why we can get to search for exponentially many hypotheses within linear time. So that's the key difference why we are exponential and non-dynamic programming is just constant, right? So, and so this is an example of merging or ambiguity packing. So merging can be thought of as local ambiguity packing. So there are some differences between these states which I would not care. For example, these states are very different in nature, right? So maybe it's different attachments or whatever, different subtrees. But if my feature only care about the last word, the root word of the last tree on the stack, then I would claim that these guys are equivalent in my feature. And I call it sushi model. So I don't care the rest of stack, I don't care the subtrees. If you don't care about them, then they are equivalent. And that's how you can manage to reduce this exponentially many guys into just one dot. Right? Of course, you can define other features which can merge more or merge less. It's all depending on feature engineering. Right? So this is why it's exponential. And this work is kind of inspired by generalized generalized LR parsing, which was very popular 20 years ago. And it was a book, and there was a workshop, but it quickly got faded away because it doesn't scale to the modern tree-bank grammars. So this is kind of statistical revival or generalization of generalized generalized LR parsing. So that's our results. So I will already show this. We are very fast, and it's actually implemented in Python. So it's amazing that these are C in Java, this is Python. And if we compare accuracy, it's also pretty good. So if you do linear time parsing without dynamic programming, that's the normal way to do, previous way to do incremental parsing. So you linear, but you don't do dynamic programming, so accuracy is not that good, right? But it's pretty fast. And our parser is a lot better in terms of accuracy. It's the same complexity in linear time, but we do dynamic programming. And we managed to engineer it so well that it's even faster than the C++ implementation, and we are in pure Python implementation. But there are some parsers which are more accurate than our model, but they require much more computational time. See, they have either cubic or into the fourth time algorithms. They do dynamic programming as well, and they're slightly better than ours. Question?
I'm just curious about the bounds.
Which one?
The complexity numbers for the Charlie and
Yeah, so they're empirical numbers. Yeah, empirical numbers, by curve fitting. So these are curve fitting, so it's curves. So the takeaway message is, if you can only afford very fast parser, so if you have to use some fast parser, then you probably should use ours. It's reasonable, accurate, and it's really fast. It's in Python, right? So some people are re-implementing it in C++, should be even faster. Okay, so any questions? Yes.
So you merge your search space into polynomials, so
Yeah.
the search is a polynomial time. What about the merging time?
Merging, it's just compare features. That's constant.
And you said it's like states are similar if we agree on features.
Yeah,
What do you mean by agree on the feature values are the same?
Yeah, so if your feature only cares about, each feature is a kind of a predicate. So the last word, the root word of the last tree on the stack, so that's solution. And you can improve more, like say the last two trees, and that will be I solution. Then these two guys will become different. But if your feature cares about less, only care the last word, then these three guys are equivalent. If you care about two words, then these two guys are still equivalent, but these two guys are not equivalent, for example. And you probably need to do a little bit of feature engineering to, figure out what's the accurate way to, do the parsing on tree-bank, for example. Yeah, question.
As long as we're following.
Sure.
So you started the talk with these classic cases of semantic language.
Yeah.
I'm nervous that the last word of my state is not such to actually capture these variables.
Yeah, so in practice we capture more. We capture the last three words and some of the subtrees, so maybe the leftmost modifier, the rightmost modifier, and a lot of the other guys. Yeah.
I think that's a driving force, the feature space that you'd actually need to be able to solve these really exactly.
Sorry?
And you think that's that the features that you're currently looking at in practice are the sorts of features that you would need to solve this example.
Yeah, some PP attachment, for example. Yeah, it's just resolved by looking at the leftmost compound, rightmost modifier.
You also look at some features in the queue, in the lookup feature, right?
In the queue, yes. In these words, right? In these words, I also have some features on the words that is just on the queue. Yes.
But that doesn't change the equivalence.
That doesn't
Because
change
if
the
they're
equivalence,
equivalent,
yeah.
they're equivalent for
Yeah, that's a very good point.
No, but I think
Yeah.
Ben is pointing out something, namely that, like, the features which are most informative for making a good decision in the future, they may end up being so detailed
Yes.
that you may not have much equivalence.
That's right.
And there's a real trade-off.
That's right.
Right?
That's
And
right.
Ben is expressing the other side of the trade-off, saying those features need to be deep enough that not much will be equivalent.
That's
So
right.
if you make it shallow enough that lots of things are equivalent, you lose.
Yes. Yes.
And that's sort of I don't know if it's an engineering trade-off, but it's a trade-off that you have to make it simple.
Yes. Yes. That's engineering trade-off, and we can even do non-exact hacking, so that we can do some fuzzy merging, which we don't do yet. Okay. In any case, you can merge, and you can merge in different ways. You can merge less, you can merge more. Okay. Any more questions? Yeah. Jason.
So you can also think of in the table in Orley's algorithm as being like a kind of graph structured stack.
Exactly. So
And you can do something rather similar with that. But can you talk about the differences between the models? It's not the same, I realize.
Exactly. So the graph structure stack, people really attribute to Tomita, but actually it's way earlier than Tomita. So it can at least we can date them to earliest parser, which is 1970 instead of 1988. So in the early chart, it's actually exactly the graph structure stack, and I think that's the best way to implement early parser. The difference between early parser and this parser is that early parser is word synchronized, and this parser is action synchronized. So that's some detail I want not go into. That's some engineering motivations into it, but they're similar in nature. This part is just easier to be well engineered to have a state of the art performance. That's the way to put it. And earlier is harder to engineer. Yeah. Any other questions? Very good. Okay, good. Let's move forward. Okay, so we're pretty good in accuracy. And okay, so the byproduct of our parser is that we can output a forest. So what is a forest? So some parsers, like maybe MST parser or Berkeley parser, outputs one single tree. But often this tree is not good enough, so you want to take, you're not confident that this is the best tree. You take the K-best trees, so Chinese parser can do K-best trees. By the way, it's also my album, but I didn't have any time to talk about that. But that's still not good. So actually you want to output millions of trees packed together in a forest. And this forest is kind of a small representation, a packed representation of millions of exponentially many ambiguities in it. And we can output a forest, and we can also output K-best trees. And then we can look at how good the forest is. So to measure the quality of the forest, we do something called oracle. So what is oracle? Oracle is the best tree in that forest or in that K-best list, according to some gold standard, right? So if you only have one tree, you're 93% accurate. But if you have 2 trees, 4 trees, and then 32 trees, the best tree among the 32 trees are a lot higher than the one best tree. So this curve generally goes a lot higher and higher, but it's kind of logarithm. It's not linear. It's logarithm because it takes twice as many twice as large k to get one more new variation. So it's kind of an exponential explosion. It's a combinatorial explosion. But if you extend this curve all the way to Philadelphia, say, then you would reach this curve. That is forest oracle. That is what's the absolute best tree in this millions of trees in the forest. I mean, you cannot afford to enumerate all of them. If you enumerate all of them, it would take you years to enumerate. But you can still have another dynamic programming algorithm to find the best tree. And for oracle, it's a lot better than the one best tree. So the forest contains a lot more kind of alternatives, diversity in it, and some of them are a lot better than the one best. Of course, a lot of them are a lot worse than the one best, but it provides some variety so that maybe in later phase you can do re-ranking on the forest, you can do translation on the forest, which I will talk more at the second part of this talk. Any questions? Very good. So now it comes to the natural question. So we know that this parser works well, but the question is how do you learn this parser from data, right? So we learn it from the tree bank, but there's a big problem. That is, so normally speaking, we use a perceptron algorithm. So that is, you do an inference, you do a search. That is basically this box is a parser, and you use a sentence. You got a tree, and you compare with the correct tree, and if it's incorrect, you do an update. So that's the normal perceptron. That's the normal way to do structured learning. But we have a big problem is that we do beam search. Although our space dynamic programming is kind of polynomial, we still cannot afford to do exact polynomial So we have to do it in linear time. And if we do it in linear time, then we have to do something very approximate. So basically, we have to only touch this kind of little beam, little kind of the yellow belt within this space. So we're not going to do it exactly. So really, in practice, it's can replace this box with inexact inference, which is our parser, which is the beam parser. And then the question is, does that still work within structural perception or other machine learning methods? Would this approximation here, or inexactness here, break down the learning properties like convergence, like generalization, like these things? So what we know is that in practice, this standard perceptron with inexact search, if we should just do this kind of same loop, it doesn't work in practice. So we have some other methods to make it work. And that's something we're going to talk next.
It doesn't work in theory either, right?
It doesn't work in theory.
But
But we show another theory here as well. More kind of specific theory towards beam search. So we kind of have a theoretical justification why beam search doesn't work with standard perceptron. And in the other paper you referred to, it's other like ALP relaxations, not beam search. Yeah. Any other questions? So we move on to the second part of this talk. That is the learning problem of incremental parsing, but it's actually more general than the incremental parsing. It can be applied to, say, tagging, to translation, to computational biology, to computer vision, to any structured domain. So it's not just NLP actually. But we motivated that from this work. That is, how do you learn incremental parser with structured perception? And the parser is very inexact. So here's like one slide overview of the structured perceptron, and it's kind of easy generalization from the binary class. You have just exponentially many classes in a structured case. So for example, the number of tag sequences or the number of parse trees are exponentially large. And so you have the same box, you have the same architecture, but the difference in the structured case is that this box is much harder, right? In the binary case or multi-class case, this box is trivial, right? And you just evaluate the two. And in this case, this is exponentially hard, right? And even if we can do dynamic programming on top of this box, in this box, it's still too hard. So we're going to replace it with inexact search, as I said, because of beam search. But then, we're going to ask these questions: what do these break, and how do you modify learning to accommodate these approximations? That's the central question we're going to ask. And is there any theory, as Jason said, behind all these? Why approximation will break down perceptron or machine learning in general, and why our modifications of perceptron works in theory? So there are two kinds of theories that we're going to answer in this talk. And then there's an empirical question that after we modify perceptron, will they work for this kind of approximate search or inexact inference? Well, we'll see. We'll see all these answers to all these questions. So our key idea is we want to train a search-specific or search error robust model. What does that mean? That means in both training time and testing time, you use the same search box. So say search box is like a parser or tagger. You treat it as a black box. So it produces a lot of search errors. But you want to train a model to kind of live with the search errors, to respect the search errors, so that even if the search is really bad, like greedy, you still want to train a reasonably correct model, so that if you plug in this model in testing time with the same search box, let's say greedy search, you want it to have a reasonable performance. So that's our goal. So we don't care how bad the search is. So most of the previous work in this area assume there are some reasonably good approximations with some bounds. But we don't assume anything like that. We say you can be arbitrarily bad search, but we still want to learn something with this arbitrarily bad search. So that's the difference. And our intuition is if search makes an error, it's because the model makes an error. Model misleads it or model misguides it. So we want to train a model to guide the search towards the true output, regardless of search errors. So that's our goal.
Let me ask you a question, but I actually want to ask it afterwards.
Sure.
But let me put it up there right now.
Sure.
So in this setup, you're assuming that the result of the inference is a point, it's one hypothesis?
Yeah, one hypothesis.
You're not, so I guess at some point I want to talk to you about whether you could generalize it if the output was a distribution on the output space.
So I guess your student, Yuan already talked to me about that
Okay.
in the meetings this morning. So how can we say do a sum instead of just one best? It's like if you want to CRF or that kind of.
Okay, so we can get to it.
Yeah. So right now we assume one best are argmax output, like perceptron and stuff. Any other clarifications? Very nice. Okay, so we want this model to live with the signals. That's the key inspirations. Okay, now if we look at the perceptron, we know that it would converge with exact search. And that's a theorem, well-known theorem, generalized from the binary case. So if it's binary case, then we say if the data is linearly separable, then we can converge in a finite number of steps. That generalized to the structure case, but structure case is slightly different. Let me just try to explain that. So structure case is the correct label or correct sequence or correct parse for this particular sentence, maybe the 100 sentence, is better than any incorrect parses. So it's 1 versus millions of the wrong guys. So it's not like positive versus negative. It's 1 versus the rest. So 1 correct parse, millions of incorrect parses. Any one of them to be separate. If they are still separable, and the theory says perceptron would converge on this structure problem in the same number of bounds, same number of mistakes. So delta is the margin large time. That's not important. Okay, now we want to look at why. So inexact search would break down this convergence, right? So this convergence assumes if you're doing exact search, then it would converge. And that's the original proof. But let me see. Let me demonstrate why. If you do greedy search instead of exact search, the perceptron would break. So this is the example. So time flies. Two words. You have noun verb. So it's 4 possible sequences, right? So if this is the space, and if current weight vector points to that direction, and so basically this is actually the correct answer. That's noun verb, right? Noun verb. And so the current weight vector is actually correct if you can do exact search. If you can do exact search, you will know that this is the best hypothesis preferred by this model, right? But if you cannot do exact search, if you have to do something greedy, let's see how it works. So if you do greedy, then these are the one step, from the beginning. You do greedy, you pick the best one. You prune that one, so this one's gone. Now from that one, you say these are 2 choices. And I'm greedy, so I picked the best one. So this one is gone. So I say that one is my answer. So that is the answer from the greedy search box. Very bad, right? It's totally wrong. And I know the correct one is that, so I do an update. So update direction for that. And then nothing changes. And next time, it's still wrong, right? So that's why it breaks. So perceptron doesn't converge with inexact search, basically. That's the typical message. Now let's look at how can we fix that. So if our search is really greedy, how can we still learn, right? So there's something, so this standard update doesn't fix the search problem. So in the sense that why it is bad, it's because you wait till the very end to do a global update, to a full update. And this update doesn't fix the search problem. So what's the search problem? The search problem is this guy's wrong. This guy is on the right path, right? So this NV, right? So you should really preserve this guy. But this guy is gone. So you should really fix the problem in the middle when you make the first mistake. Instead of waiting till the end, you didn't fix the problem. Or in other words, the model is actually correct, but your search is wrong in some sense. Now, let's look at something in the literature called early update, which is kind of a very popular method in inexact search. So early update says, I want to update at first mistake, basically in the greedy case. So suppose you're doing tagging, and you basically tag all these previous words correctly, and maybe the 10th word you did wrong. You stop and update on this prefix and skip the rest of the sentence, and you move on to the next sentence. So that's their intuition. And let's see why it works. So this is start, okay, and because model prefers that, you print that, right? Now you realize it's wrong, right? So it should be N, but I got V. You stop and do update. You don't care about the rest, okay? You do nothing. If you do that update, your next wave is actually pointing that direction, and it's actually correct. So this shows that early update is actually correct, because the intuition is early update fixes the search problem in the middle. So it's a real problem that is being fixed. But there's no theory behind this. So early update is proposed in 2004, and it's been very popular afterwards, but nobody knows why it works, right? Why it works better than standard perceptron. So why would early update work well, and why would standard perceptron doesn't work well? So there are several questions behind these two questions, behind these 2 points, but there's no theory yet. And we provide this first theory, justification for these 2 problems. And there's a third problem we're going to address, that is, can we do better? Is early update the only possible way for inexact search? Actually, it's not. We show that early update is actually a special case within a large framework, within a more general framework called violation fixing perceptron, where you can, I'll show you in the next few slides, But the other problem we're going to address is early update learns too slowly. So early update works in practice. It converges. It's like unlike standard perceptron, it doesn't converge, but it converges a lot slower than standard perceptron. So if standard perceptron, normally speaking, converges in 5 iterations, early update would take 50 iterations to converge. So I cannot afford to run 50 iterations of parser over the whole tree bank. So definitely not possible. So we're going to address this problem.
Yeah, it seems to me that there might also be another problem with early update besides convergence, which is it might not get you a good loss. Is that right? So what if you could have an early error, and if you have that early error, then you're much better thereafter. Because, in other words, if a good policy isn't actually achievable with your feature space,
right,
then it could be that this business that biases toward minimizing errors early on might not be the globally best thing to do.
Right,
that's not how you're evaluating loss.
Right. So perceptron is 0, 1, so it doesn't differentiate different values.
Yes, okay.
Right. And the other point is, I only showed the greedy case, but actually there's a beam case, which is more general than that. And you can be a little bit incorrect in the beginning, as long as you survive in the middle, it's fine. So I will show that.
You mean in practice, it's fine.
In practice, yeah. There's a beam search side after that. Okay, so the high-level intuition why early update learns so much slower is because it only updates on prefix. So it learns partial examples. It doesn't take advantage of the whole sentence, right? So although it works, it kind of takes a lot more iterations to learn the data. So let me do some little bit of theory behind this. So we're trying to answer these questions: why early update works and why standard perceptron doesn't work. Let's do that questions first, and then we can generalize. So if we look at the convergence proof of the original perceptron, so we say why exact search would work, would converge. If we look at the proof, which I will not show today because I do not like the equations on slides, there's a surprising observation that convergence proof does not require exact search. I mean, normally people think convergence requires exact search, but actually it's not needed. What is really needed is only a much weaker condition called violation. So what is a violation? So let's say our current wave vector points to this direction, and we pick this guy as the correct guy, as the best guy, but this guy is incorrect, and this guy is correct. So you want to do an update towards that direction to kind of pull it back, so that next time you will be more likely to pick the correct guy. So that's an update. And so what is a violation? It basically says the incorrect label is scored higher in your current model than the correct label, which should not be the case, which is something you want to fix. So that's called a violation. And as long as each update is on a violation, the perceptron will converge. So that's the proof, really. But what's exact search? Well, exact search is really not needed, but exact search is used merely to guarantee a violation. If it's exact search, it's of course a violation. But you don't need to be exact search to be a violation. For example, all these guys beyond this line, which is perpendicular to this wave vector, are violations. This guy's violation, this guy's another violation, this guy's another violation. You don't need to pick the argmax. You don't need to pick the one best. You can pick this guy. As long as it's in a higher score than the correct guy, it's something you want to fix. So in a sense, as long as we can guarantee violation, you do not need exact search. So that's the key observation which people overlooked in the past. Then we're going to ask why inexact search breaks the proof. Well, exactly because violation is not guaranteed for each update. So for a lot of updates, it's not a violation. Let's see why. Okay, so this is a case of the previous update. If we just do greedy search with standard perceptron, and this is your update direction, and that's not a violation, right? Because the current wave vector actually prefers the correct sequence, prefers the correct label, so it's not a violation. In the sense you're not correcting it. Like the model itself is actually correct if you can do exact search. So this is not a violation, right? And if you do early update, it's actually guaranteed to be a violation. So that's another key point. If early update is towards that direction, and so the current wave model will pick some prefix that is incorrect. So that's on the prefix level, that is a correct violation. And it's intuitive because up to the first error, you can guarantee that it is a violation because this is the case where the incorrect guy scores higher. The incorrect guy scores higher than the correct guy. So it's guaranteed to be a violation at the first mistake. After that, a lot of things can happen, and you cannot guarantee violation. So that's the high-level intuition why they invented this, but they didn't have the theory behind it. But we provide the theory. Okay, so So this is, again, so if we can guarantee violation, we don't care about exactness. So we propose some new framework called violation fixing perceptron, which is replacing this exact search box by a box called find violation. So you just give me an example, I find a violation update. That's it, right? As long as I can do that, I can guarantee convergence with the same mistake patterns. And then we show why early update works in theory is because we can show it as a special case of violation fixing perceptron. As I said, early update, each update is guaranteed to be violation. So this is a more general case than a greedy search. As Jason said, it could be a beam search, like what we did in parsing. And in a beam search, we update not at the first error, but at the first time the correct label falls off the beam. Okay. So this is the time the correct label falls off the beam, and you have to stop and update, right? And at this time, you update like this, the correct guy versus the incorrect guy. And of course, the correct guy is scored lower than the incorrect guy, which is the violation. But afterwards, anything can happen. It could be at the end, the correct guy is actually scoring higher than anything incorrect, beam, which is not a violation. If you still do a full update, it's not a violation, as the example I showed before, right? But up to this point, you can guarantee that. Afterwards, you cannot guarantee that. So that's the high-level intuition why Hopkins and Rock invented this mechanism. Okay, so we showed it converges within this framework. But then we're going to also address the point that, is there anything else that we can do? Is early update the only method? Of course not. We can do a lot of other things. So I propose 3 new methods. So the first method is called hybrid. So hybrid is basically the hybrid between early and full update. So a full update is a valid violation, you would do the full update. If it's not a violation, you would do it early. So that's guaranteed to be valid. Or you can do the latest violation. So this is the earliest error, this is the latest violation. And of course, it's guaranteed to be violation, to be correct, to be valid updates. But the most important, interesting thing that we invent is called max violation. So that's the single point in the search space where your error is the worst, the most severe, the biggest error. It's intuitive to correct this error first, because that's the kind of worst error you would make. Okay, so not the first error, not the last error, but the largest error. So what we call max violation update. And we show in practice that this one works best. This one converges a lot faster than early update. So let's look at some experiments. I have 2 sets of experiments, one on partial tagging. So that's a proof of concept because you don't really need exact search because exact search is already pretty fast. But in incremental parsing, the first part of this talk, is the real problem.
Before you go on to the experiments,
Sure.
I'm still trying to understand something about the generalized perceptron framework.
Sure.
So, can you talk about how we should think about partial examples here?
Yeah.
I mean, your scores are on. Should we think about individual actions being classified, or the entire
prefix?
Okay, so you're thinking of every prefix as a separate example.
You can think of that way. Yeah, so that's one way to view this one. You enlarge the training examples to include all the prefixes.
Right, but then you end up with bias toward longer sentences or something like that.
Oh, so basically the separability says any correct prefix should be better than any incorrect prefix of the same length.
Yeah, so all of this is only in the separable case, which is really what I was asking about before when I talked about logs.
Right.
Yeah, okay.
So we define separabilities to avoid that.
Yeah.
But I will not go into details. Any questions? Okay, so let's quickly look at some experiments. So first is partition tagging, and that's really easy. That's just trigram in a perceptron. And in this case, we do a beam search of 1, 2, 3, or 10, or infinity. And the difference is between standard update and early update or max violation update is really most pronounced at the smallest beams, especially beam 1. So beam 1, there's a huge difference between standard update and early update or max violation. Why? It's because if you are beam 1, your search is really bad. You have a greedy search, so you made a lot of search errors. If you made a lot of search errors, then the number of invalid updates, so we can actually count the number of invalid updates, the percentage of invalid updates in your learning. And it turns out that more than half of the updates are indeed invalid, meaning they're not on a violation. So they're bad updates. So that's exactly why it works so badly at beam 1. But afterwards, it quickly drops to 0. So afterwards, it doesn't make much difference. Okay. But for parsing, it makes a real difference. So for parsing, the baseline is actually early update, because people actually know that standard update doesn't work well. I will show you that in the next slide. But early update, that's the way I used to do. It takes too long. It takes like 40 iterations or 16 hours to converge. And if we do max violation, it converges a lot faster. 10 iterations you reach the same point or a little bit better, or 12 iterations you reach even higher point. So you can reduce the training by about 3-fold. So that's a significant reduction of training time, because this is just too slow to do. And then we have a question like which I glossed over before. That is, in parsing, the baseline is actually early update, whereas in tagging the baseline is standard update. So why standard update is working really badly for parsing? Actually, nobody tried this, but I just tried it, and it works horribly. So the difference between early update or maximum violation isn't that big compared to the standard update. So the standard update is terrible. Why? So if we look at tagging, the difference is mainly on the first beam. But if we look at parsing, even if the beam is the biggest, it's 8, you still make that it's still horrible for standard update. So the reason is because the number of invalid updates is different. So, or in other words, the difficulty of search is quite different between these two. So tagging is really easy to search, and parsing is really hard to search. So for tagging case, the number of invalid updates quickly drop to 0 because the search error is really not that much with larger beams. But for parsing, even at biggest beam, you have half of the updates invalid.
So is there really enough test data to support like 4 significant digits here? Like I'm going to implement max violation rather than early. I want to make sure that those numbers are working. Right?
Yeah, that's not important. The difference between this and this is too small. The difference is really between the number of hours you need to train.
Right.
So I can afford 16 hours to train a parser. If I want to ship my parser to RE and need 1 trillion hours in machine translation data, you should prefer to train it only 5 hours for that. So the difference between this accuracy is not the important part. The particular message is the speed of training. And a standard update is really bad because if your beam is 1, almost all updates are invalid because you make huge number of search errors. Even if you have a big beam, still half the updates are invalid. And this number doesn't go down very much. So I tried to go larger, it doesn't go down very much. So basically, it's like parsing is much harder to search because the search space is so much bigger than tagging. Even if it's dynamic programming, it's still a lot larger than tagging case. So the takeaway message is, if your search is bad, try our methods. If your search is not that bad, you don't need to bother. But the worse your search is, the more important our contribution is. Or yeah.
And just like the right intuition here, this is hugely a function on how you're collapsing your states.
Yeah, exactly. So if I have edge factored or less accurate less expressive factorings, and if I converge more, then this space is smaller, and then these guys will go up.
And there are other ways of merging your spaces, so this will be exponential search space, right?
Yes. You could imagine this is exponentially larger as well. Yeah. Any other question? Yeah.
What prevents you from updating away from all the errors together and parsing example?
It's hard to prove the convergence. I tried to prove it. It doesn't.
But you could just try without it. Sometimes there's empirical. Did you try doing that?
That's right. Yeah. So I should try that. Yeah. But I want to keep my updates as simple as possible. Just update one pair of for one validation.
I have a question.
Sure.
So if you think about this global perceptron that you're learning, right?
Yeah.
And the partial level, if you think about it as a local perceptron, if you still have separability on the local level perceptron, you can prove the convergence there, right?
Yeah. So another way to do it is
because if its features are separable on the local level of the perceptron, then you will learn how to sequence on the local level, get rid of ambiguity, and you can still prove the convergence.
That's right. So that's basically the idea of how we do the proof. So we kind of redefine separability to say it's separability among prefixes, basically the local one. So, but the search itself is structured. So we're not just back into unstructured perceptron. But the proof looks like it's unstructured. That's kind of another way to look at it. Any other question before we go to you should 5 minutes.
What's the time?
Okay, great. So recap for this part. So we had 3 main contributions. It's a framework of perceptron, and we showed previous work as a special case and provided first theory for it, and we have new update method which was a lot faster than practice. So in this talk, I covered these two the first parts, and the third part, which I probably didn't have time to cover, I would just quickly say something about it. It's syntax-based machine translation, and the way we do it is same as the way human beings do it. So we kind of understand it as parse tree, and then generate the string. So it's also the same way as compiler does it. So it's about syntactic direct translation, it's about statistical syntactic direct translation, and roughly speaking, that kind of parsing to source syntax and that, and we can do. So quickly we walk over this example. So this is Ba Wei Yu Sharon. The Caldwell, the Bush with Sharon had a meeting, and which I'm translating into English. We have rules like this, two-string rules, and we have Bush is something, and Bush will be Bush. And then the something part of the verb phrase has, with somebody, choosing a something, goes to how something with somebody. So pattern match it, and then we do that. And then we do that, and so it's just recursive conversion of the English trees to the Chinese, the Chinese parse tree to the English sentence. And it's really simple, but it's not that well in practice. So we want to replace that part by k-best trees, because the first best tree is not necessarily the best case. So that's the k-best trees, but it doesn't solve the problem because, as you know, k-best is only tiny fractions. You want to do a forest, so that's our forest-based approach. And it's basically, packing two trees in the forest, and then you can do pattern match on a forest. And I'll quickly walk over that. I'll just show you some results. So one best tree, you have some low quality, and k-best trees are better in translation quality, but takes much longer. The forest is very fast, but it's still a lot better. So almost 2 points over one best is very significant, and it's even faster than 30 trees. So this forest has millions of trees in it, but it's faster to translate millions of trees together than translating top 30 trees individually.
And that forest comes from the graph structure of snack in these experiments.
It could eventually do that, but this is the kind of Chanya. But eventually, we want to do that. Yeah. So it's fascinating. This is because dynamic drawing again, right? So, and then we'll ask. This question is kind of interesting. So, what's the percentage of how often is I's best tree picked by the decoder as the best tree to derive the translation? And most likely the first best tree is the highest quality. So 25% of the time you will pick the first best tree. But quickly goes down to 0 and stops at 30. But if you use a forest of millions of trees, it has a much longer tail. So 32% of the time you pick a tree that is ranked worse than 100. So you wouldn't do that in parsing. You think these trees are rubbish, but in 20% of the time you have a tree, you use a tree that is ranked below 1,000. So this shows that regardless of how big a k is, the k-best list cannot catch up with the exponential explosion of the search list. And the forest can do that. So that's the message. And we can also do extractions on root extraction on forest. And so this is the forest squared approach. So translating on forest and using roots from forest. And that's a lot better, that's 2.5 better than one best. And it's also significantly better than Pyro. So this is David Chan's implementation of Pyro. And this is an example. Paulo said he's leaving for alpha is very important. That's correct, and these two guys are not correct. And let me just quickly say something about impact of this approach. And it's actually, if you use Google Translate, you will notice that the translation quality of English Chinese improved a little bit recently, just because they actually switched to this system. So this forest-based system is the current best performing system within Google for many language pairs, including Chinese and English Chinese. Some internal news, but actually this is a production system. If you try it online, you will notice that. So Bush and Shaolin will got exactly the same, exactly correct translation. So my parents have been using this Google Translate for the past, say, 8 years or so, because they don't speak English and they want to monitor my webpage. Did I publish a new paper or something like that? So they constantly notice, progress in translation quality in Google Translate, and they're proud that it got better because of my approach. And okay, so bigger picture. So I want to move towards more structures and more machine learning. But what I do is also kind of statistical revival of the old stuff that happened in role-based MT many decades ago. And to conclude, so we eventually said, well, I have two questions. Can we understand language or can we translate language the same way human beings do? And the answer is yes. We can do efficient dynamic programming and structured learning to get fast and accurate parser in bigger times in the expansion large search space. And we can also do that for translation in the syntax and forest-based translation system. but we're not there. So the common theme of my work is efficiency and incrementality. So something I didn't talk about is we can also generate translation in linear time incrementally. So efficiency and incrementality. It doesn't mean that my work is incremental. It means that my processing of natural language is incremental. Not my work is incrementality. But I like efficiency. So basically, but we're not there yet because this representation has to be more like semantics, but we currently just use syntax. So that's maybe the most important future work in this direction. So the big picture is I do, these two guys to help NLP and makes it happier, and I give back to machine learning as well. So I'll stop here, and if you like the future work, I can talk about future work, but I can stop here if you want to ask questions.
Thank you.
And then also just a quick administrative announcement before we ask Liang more questions. So if you're going to go to Dan's Caldy seminar in 15 minutes and you haven't gone to pick up your lunch, you're invited to leave now and go do that so you can make this seminar on time.
So, thank you very much in incrementality.
I had a quick question. I don't know if you want to discuss it with people later. I was wondering whether the unnecessary updates you do in the standard application.
Yeah, you can avoid that.
No, whether they lead to overfitting. Avoiding them is not simply because you want to convert to the algorithm.
Yeah, it's possible.
But because it might lead to overfitting.
It's possible, yes. It's possible.
Do you have any
No, I haven't. My theory, like I look at a proof and I see this breaks down proof.
Okay.
So, but yeah. So the thing I want to do next is this kind of direction. Semantic parsing and semantic-based translation. Syntax-based translation.
So what's your representation of semantics going to be?
So currently it can be like just lambda calculus, but I want to do it incrementally. So it's important that you introduce that sentence incrementally and use semantic disambiguation along with syntactic disambiguation. For example, what is the largest state? We would say Alaska. So that's the lambda calculus. But if I say what's the largest state bordering Pennsylvania, that's probably New York. But no, I'm not finished yet. But if I said south, that's probably Maryland or something. So you want to kind of incremental understanding in the semantic representation. That's something people don't do today. And we can use it for question answering and image translation. So that's one slide overview of future work. I also do that. This is a sidebar from Maria. Syntactic language model, which is Fred was very motivated for. And I also do word alignment. Word alignment by quite a lot. So a student of mine ACL, and we can reduce the gap abstraction by a lot by using sparser models. So it's on top of that. But it's a shame that we still use word alignment. So what I really want to do is to learn to do translation without word alignment. So it's a shame, I think, that so far machine translation is still based on technology invented 20 years ago by the IBM people. So they already went to Wall Street and earned a lot of money, and we're still here, doing MT research. So it's kind of a shame that we still do that.
Why do you think that you should? Why do you think you should get rid of word alignment instead of using word alignment as a part of something more complicated?
Because as a native speaker of Chinese, I try to align data English Chinese. I often find it's almost impossible to align data. It's like word alignment to me is is ill-defined problem to start with. It's not a real task. Translation itself is a real task. People do translation all the time, but nobody does word alignment. Well, maybe some content words can have some alignment, like bilingual dictionary. But to me, it's like the syntactic and semantic transformations, the slightly non-literal translations. These things cannot be modeled by word alignment. So, yeah, to me, it's not a well-defined task. It's just a step that we do in the middle, but it's not necessarily a step we should do.
Yeah, you could say the same thing about segmentation in phrase-based models.
Exactly.
The segmentation boundaries you couldn't get annotated agreement on.
Yeah, exactly. Yeah, so anything you cannot get annotated agreement is not real to me. And people have been trying to do that, but not very successfully. Like in Mark and Wong's work and Chris Dyer's work, doesn't scale very well.
So you say anything that you get agreed on isn't real, but a lot of those ambiguities that we're talking about right at the beginning.
Yeah,
Those are real ambiguities that happen and people are going to disagree on them.
Exactly. So parsing is not a real problem. So we do parsing because we think it's useful in translation, but if we could do something, eventually it's so we kind of do something semantic based. So maybe we don't need a syntactic parsing to start with. So and the semantics is not real either. So people don't agree on the calculation. There's no answer to that. But I think word alignment is the most unreal task. So if we'll not
I want to push back a little bit on the parsing and semantics update. I mean, you're joking, right? Okay. Teresa, you mean if there's not any context, people don't agree. But so whoever's saying that has a particular parse and a particular semantics that they're intending.
Perhaps, yes.
I mean, it's real in that sense. But when I'm speaking to you, and you want to or if I translate a sentence from French to English or something like that, I wasn't intending a particular segmentation or a particular alignment necessarily. I mean, you might argue that there are clumps that align here to here, but the word-to-word alignments
Yeah,
are
I was
not
thinking
quite
more along the lines of some of the tasks that I've been involved with egalitarian. There's natural ambiguity there.
Yeah.
I think she might be talking, when we have a conversation with my wife, she might understand something completely different. Like I was gonna clear.
Yeah, I think you have to marginalize over the interpretation. But there's a real distinction in your disagreement about what you actually meant.
Yeah.
Okay, so thank you.
Just a quick announcement, if you haven't signed in, the sheet